So welcome to our series on gases, and today we're going to look at pressure. So gases are all around us. Given that gases are invisible, we may not think of them directly, but we're certainly aware of their properties. Think of the mixture of gases we breathe and call air. We feel the wind on our face. We burn gases when we're cooking. So what do we know about gases? We know they tend to have a low density, so they float above the surface of the earth. We know they can be compressed, such as aerosols, like your deodorant can. They can expand when heated. This is what causes wind. Gases are absent of structure, meaning they have no fixed shape or volume. Gases will expand to fill a container. Particles move around almost totally independent of each other. They consist of rapidly moving molecules that are relatively far apart. Gas particles do not have much effect on one another unless they collide with each other. They have little attraction for one another, so they tend to move about quite freely. Gases fill the container that they're in, so its volume will become the volume of that container. The volume is highly dependent on conditions to which the gas is subjected to. So if you really want to know the volume as a measure of the amount of gas, then it's also necessary to know the temperature and the pressure of that gas. So this is the first time we're introducing pressure. What is pressure? Pressure is the amount of force applied per unit area. This can be written mathematically as P is equal to F for force divided by A for area. So pressure is equal to force divided by area. A tremendous pressure can be exerted by a moderate force if the force is applied to a small area. A good example of this would be to compare if you were to wear a pair of stiletto heels versus a pair of boots, and to compare which heel will wear faster. So if you're the person wearing both types of shoes, what you will find is the same amount of force is being applied to both shoes, to both heels. But the stiletto heel, we have a much smaller area compared to the heel on the boot. And as a result, or anyone who wears stiletto heels on a regular basis will tell you you've got to have your stiletto heel re-heeled an awful lot more often than you would a boot, because the heel will wear a lot faster. The reason being the pressure applied to a stiletto heel is much, much greater than that of the boot. Even though the force may be the same, the area is different. So when I have a smaller area, it exerts a greater pressure than if I have a larger area. So SI units, which stands for Standard International, the unit measure for pressure is often pascals, which is newtons per meter squared. Gas has a pressure because its particles bump into things, and as a result they exert force. That force is often called an atmospheric pressure. So 1 atmosphere is the pressure at sea level. So most of us who live at sea level will be experiencing 1 atmosphere of pressure on us. If I want to measure atmospheric pressure, a barometer is often used. So a barometer is a tube closed at one end, filled with liquid mercury, and inverted into a container of liquid mercury. The height of the mercury column adjusts to equal the atmospheric pressure exerted on the pool of mercury. Thus, changes in atmospheric pressure cause changes in the height of the mercury column. Barometric measurements of mercury are commonly used to express atmospheric pressure. So here we can see that 1 atmosphere is equal to 760 millimeters of mercury, sometimes called torr. So you could say 760 torr, which is also equal to 101,325 pascals, which we know is measured in newtons per meter squared. So there's a number of ways of expressing pressure in atmospheres, in millimeters of mercury or torr, or in pascals, which is newton per meter squared. Given that pressure of gases in chemical systems are often a fraction of 1 atmosphere, they tend to be measured in millimeters of mercury, as I said, also called torr. So how big is atmospheric pressure? Atmospheric pressure is huge. You don't feel it because it pushes from all directions. Right now, atmospheric pressure is pushing on your chest, but the gases inside your body are pushing back with equal magnitude, and as a result, you don't feel the pressure. Where you might become aware of pressure is if you're in an aeroplane. So when you're in an aeroplane and you go up into the atmosphere, the pressure decreases, and often you'll feel a slight pain in the ears. The reason is, in the cabin, the pressure has dropped. However, in your ears, the pressure is still what it was before you took off. So now there's a higher pressure inside of your ear. So in order to release that excess pressure, we would often just wiggle our jaw to allow it to escape from the ears. And then we have equal pressure now both inside and outside of the ear. To really get an idea for the true magnitude of atmospheric pressure, there was an experiment conducted by Guericke known as the Mandelbrot experiment back in 1654. What he did was he made two metal hemispheres with a good seal between them so that no air could seep in or out, and a valve which allowed him to pump air out of the interior. When the sphere enclosed to a near vacuum, he found that when he got horses, they could not pull the two halves apart. The only way the two halves would come apart was when he allowed air back into the hemispheres, and then they came apart very, very easily. The explanation for this was that the air pressure on the outside of the sphere pushes the two halves together. Only when there is air pressure on the inside pressing outward with a balancing force can the hemispheres be easily separated. So this is the same way that a suction cup that you would put on glass works. So you put your suction cup on glass and you press it. You push out some of the air, thereby reducing the air pressure on the inside of the suction cup. And if you pull on that suction cup, provided it has a good seal, you'll see how strong it is. What's really happening is it's the air pressure on the outside holding and pushing the cup onto the glass. It's only when you break that seal and have equal pressure on both sides does the suction cup come away from the glass. So I hope this has helped to explain pressure in terms of gases. So thank you very much for listening.